So what's interesting about this is if you look carefully to find out where three planes meet, so long as they're not all parallel, two are parallel. Two are parallel if their normals are the same or have the same multiplier. But if they don't, they will only meet in one line of intersection. Well, that line of intersection is shared by the two planes as well. So you don't have to figure out the third plane if you don't want to. You just need to figure out the two. So I don't quite understand the purpose of his question here. If we look carefully, if we look at the coefficients of these first two, we get 1, minus 1, and 1. And we get minus 1, 1, and 2. So they are not the same normal. So they will not be parallel. If I'm finding for x, it's minus 2, minus 1, so minus 3. If I'm finding for j, I have to make the sign negative, so I get 2 minus minus 1, which is 3, so it's minus 3. And if I find for z here, it's 1 minus 1, so that's 0. So that is the directional plane for the line of intersection, because when I cross multiply the normals, I get the directional of the line of intersection. Now I just need to find a point on either line. To do that, you can set x to equal to 0. When x is equal to 0, we get this. If I add them together, I'm left with 3z is equal to 3, so z is equal to 1. So that means one of the points is x, 0, comma, we don't know y yet, 1, but we do know 1. If I put in z over here when x is 0, so 0 plus 1, bring the 1 over here, I get minus y is equal to minus, or is equal to positive 1, so y is equal to negative 1. So I get 0 minus 1, 1 is a starting point. 0 minus 1 and 1 is a starting point times t minus 3 minus 3 comma 0. That is the line of intersection that defines it. If you wanted to find another point and prove it, you could take t of 1 and find another point. So that's 1 point. And another point would be when t is 1, you get 0 minus 3, so you get minus 3. You get minus 1 minus 3, you get minus 4. And you get 1 times 0, 1. So it looks like the z-axis will stay at 1 no matter what. So let's see, to prove this, we can go to our graph here. Okay. And we can put in one of the points if we want, or we can ask it to draw a line. Equals line. And then we're going to, the direction vector thing doesn't work very well, so we're going to do point comma point. We're going to use the point of origin, or the r naught, and you have to put it in brackets. 0 comma minus 1 comma 1, then close brackets, then open brackets, and put in your other point, minus 4 comma 1, close brackets, and then click elsewhere. And it will draw the line. Oh, it did not draw the line, so we have to delete it and try it again. So this thing is very finicky for drawing lines. So I have to choose line, I have to choose point to point. And I have to open brackets, first point, 0, comma minus 1, comma 1. Second point, minus 3, comma minus 4, comma 1 again. And we'll draw a line now. Hopefully that's our line of intersection. And look at that, it is. So what's weird is, why in the hell would you ever cross vector three planes when they must meet where two planes meet? That's my question. And I would also never use a cross vector to find a point of origin when I can just set x to equal 0. It's very easy to set x is equal to 0. I'll try to look up his method of cross producting endlessly to get the line of intersection. I just don't think it's valid. So to run through the steps again, Where three planes meet is the same as where two planes meet. So step one, find the normal. Normal 1 is equal to 1, comma minus 1, comma 1. Normal 2 of the second line, the two easiest lines to use, 1 and 2. Second step, it's the same as that other question. The cross product of n2, n1, n2 will be the same as the directional vector of the line of intersection. That's because the cross product is perpendicular and the line of intersection is perpendicular. So when you find the perpendicular of this, you're finding the parallel of the line of intersection, which is a direction vector. So you do exactly what we do. You do cross product. So it's minus 1 times 2 minus 1 times 1, comma, and this one you have to multiply by minus 1, and it's 1 times 2 minus 1 minus 1 times 1. Very confusing there. And then the z is 1 times 1 minus 1, which is 0. When you solve this, it's minus 3, or minus 2 minus 1, which is minus 3. When you solve this inside, it's 2 minus 1, which is 2 plus 1, which is 3. But you have to multiply by the minus 1, so you get minus 3. And that's the directional vector. To find a point on this line, use the original equations. Set x is equal to 0. Why can you do this? Because a three-dimensional line will eventually pass through the x, y, and z coordinates unless it's parallel to x. In this case, it is clear it's not parallel to x because the x values are different. You cannot set z to equal to 0 because z is equal to 1, or z is already equal to 0 in the directional. So you'd have to set x. When you set x to 0 and you solve it as I show in the video, you discover a point of origin is 0, comma minus 1, comma 1. If you were to write that in as its scalar, it would be x is equal to 0 minus 3t, y is equal to minus 1 minus 3t, and z is equal to 1. And if you look at your answers in this, it's very similar. Oh, by the way, because there is a 0 here, I could change these to just minus 1. That's my bad. You can make this minus 1 and this minus 1 and this 0 because they can all be divided by 3, which explains why this is plus 1 and why this is plus 1. You might say, why is my minus? That's just in a different direction. If you have a line like this, you can tell it to go this way, where all the signs are opposite, or you can tell it to go this way. This way here would be as I have it, minus 1, minus 1, 0, and this way would be 1, 1, 0, which is what the answer is over here. Either answer is correct. It doesn't matter where your direction vector is if you're telling the line to draw it that way. Oh, and if you needed to write it, I don't know if he wants you to rewrite the line in terms of a point between 2 points, but you could. This you tend to write the scalar projections or the vector projections instead. Hope that helps.